All right, so again, last time we discussed how to find volume of solids, but the solids were already given to us, okay? So all we needed to do is be able to figure out what's the cross-section. So when you make a cut to the solid, we need to know what's the area of the cross-section, and with that information, we're able to calculate the volume. Now, this time, let's discuss another method, which have to do with how to find volume of solids of revolution. So let me explain what's a solid of revolution. So a solid of revolution is obtained when you take a plane region and you rotate it about a fixed line, okay? So when a plane region is rotated about a fixed line, this is called axis of rotation, typically. Axis of rotation, the solid generated is called solid of revolution. Okay, so I'm gonna attempt to draw something. And again, you have to activate your imagination here and activate your imagination. That's all I can say. So imagine that the region that we want to rotate is something like this. Okay, so this is the region that we are rotating. Let's call it R. In fact, I'm going to even include this. And then let's rotate this about the x-axis. So let's say that our axis of revolution is going to be the x-axis. So they're going to be rotating like this. So naturally, if this is the region that we are trying to rotate, what's going to happen is, first of all, that we're going to have some sort of reflection here. Let's see, there's another color for the reflection. And then I will attempt to imagine the x-axis being a mirror, and then this sort of shape will be created. So again, you have this plane region, and then when you rotate this around the x-axis, you're going to create a solid. You can more or less picture your solid. So think of it as being, I don't know, like a place to put flour, but it has this base, and then it has this thing, and you can put the flowers inside. Do you understand what I'm saying? I'm not good at drawing, so this is as good as it gets. Okay, so make sure that your imagination is there for this. Anyways, for example, if you were to rotate half a circle, doing this, if you rotate half a circle around the x-axis, what do you create when you do this? You're gonna create a sphere, okay? So it's like that, and then you're gonna create a sphere. Can you picture this in your mind? That rotating half a circle makes up a ball. Yes, so that's what we're talking about. Okay, good. So this is and this is the type of solids that we're going to be discussing. The question is, how do we find the volume of something like this? Okay, how do we find the volume of a solid that's generated in this way? Now there will be two main cases. Okay, sometimes solids will have holes in them. They will have some hollow part, and sometimes they don't. Like this one doesn't have a hollow part. Okay, how do you know that? Well, notice that in this case, something typical. What's going on is that the region that we are rotating is completely adjacent to the axis of rotation. There's no space between the region and the axis of rotation. If you happen to have a space, then there will be naturally a hole created. Okay, we're going to discuss that later. Right now, let us deal with the case in which the region that we're rotating has no hole. Okay, so the volume, the solid that results doesn't have any hole. All right, so let's write some stuff down here. So the goal is to find the volume of such a solid. To find the volume of such a solid. Okay, so before we try to analyze an arbitrary region, let us try to analyze what happens when we rotate a very simple region. And for us, the simplest region that we can analyze is a rectangle. Imagine that the region that we are rotating is a rectangle. What type of solid do we obtain? What is it? Okay, so let's see. I will attempt to draw it. So a rectangle. Okay, yeah. So suppose that our region R is a rectangle. Okay. And let's say that the rectangle, you can place a rectangle in different ways, and you're going to see that actually there are different methods to calculate volume, and it all has to do how you decide to place a rectangle, because there will be a rectangle that we're going to be placing in cases like this as well. But right now, our region is a rectangle. We're going to place it perpendicular to the axis of rotation, okay? If you place it parallel to the axis of rotation, you get something else that we discussed. That's what happens in 2.3, okay? Right now, we're going to place it perpendicular to the axis of rotation. So we have a rectangle, and it's perpendicular to the axis of rotation. All right, so let's see. Here we have a rectangle. Let's say this is our rectangle. And then we have our axis of rotation here. And in the example that we're going to do now, there is no gap. Okay, so there is no gap between the rectangle and the axis of rotation. So it's right next to it. Okay, they are adjacent. And then we're going to rotate about this line the way that I'm showing here in the picture. So there is some quantity that we are interested here. Okay, so I'm going to call this distance right here, the height, if you will. I'm going to call it R. And I'm going to call this the width of the rectangle. Let's call it delta W. Okay, so if you have this rectangle, and if I rotate that, what sort of solid do we get? Let's see, think about a line. If I have a line and I rotate it like this, you get a circle, right? But now this is a circle with some sort of thickness to it. We call this a disk. This is called a disk. Just think about this, okay? That's what we get. So after rotation, so rotate, and then we get what we call a disk. So what I'm about to describe to you is how to find volume using the disk method, okay? But you will see why it's called that. So we obtain a disk. Let's see, get this guy. Then I'm gonna come all the way down here, and we have this. Okay, so we have this sort of, and then here is the center of the disk. Okay. So hopefully, do you agree with this? So again, here you have your rectangle, okay, and then when you rotate that rectangle, then a disk is created. Now, here there are some important information that we need. When you have a disk, you want to know what's the radius. Now, the radius of a disk is exactly that quantity R that we have in the picture, right? So the length of this rectangle stands for the radius of the disk. Do you understand this? And then the thickness of the disk is delta W. Okay? All right, so this is the simplest solid for revolution that you could get, a disk, and it's produced when you rotate a rectangle that's perpendicular to the axis of rotation. What's the volume of this? How do we find the volume of this? So volume, we are interested in the volume of solids of revolution, so we want to know what's the volume of the disk. So this is a uniform picture, right? So if I make a slice, I get a circle. That's a cross section. So how do we find the volume of a solid that's uniform? Area of the base times the height. This is exactly what we were talking about last time, right? You get always the same circle. The circle is not changing, okay? You get the same circle no matter where it made the cut. So the volume here is area of the base times the height. The area of the base is a circle, so that's going to be pi r squared. And then the height here really is the thickness, right? The width of this. So pi r squared times delta W. Do you understand this? Okay, so that's the volume of the disk, and this is how you find the volume of this solid of revolution. Again, let me, I guess, write down here in words what I just said. So this is area of the base times the thickness. Whenever you have a solid that is uniform like this, that no matter where you made the cut, you have the same cross section, exactly the same. This is how you can figure out the volume. Okay. All right. So now, okay, that's very good. But how can we use this idea to, for example, calculate the volume of something like this? Okay. So let's talk about that. And you know, the idea is actually pretty simple. Let me imagine that before I start making the rotation, I approximate this rectangle, this region with a bunch of rectangles, like what we did when we were calculating area, right? Imagine that I fill this with a bunch of rectangles, and then when you start rotating, what's going to happen to the solid? It's going to be filled with what? With a bunch of this, right? So that means you approximate the area with rectangles, so after rotation, your solid, the volume of your solid will be approximated by adding the volumes of all of this that we're calculating, right? And then what do you think is going to happen? We're going to take infinitely many rectangles, and then we take a limit, so an integral is going to pop up, right? Because when you add all of these things infinitely many, then that becomes into an integral, and basically all we have to do is integrate the formula for the volume of a typical disk. Okay, that's what's going to happen here. That's what I'm about to show you, okay? But you understand this, right? You rotate, a disk is created, and all of these disks approximate the volume. So number 2, so that was case number 1. Rotate a rectangle, we know exactly what happens. So case number 2, let's say that we're going to rotate a region, not necessarily a rectangle, but what we want is this to be adjacent to the axis of rotation. Okay? So what I mean by this is that after rotating, you're not going to have any hole on your solid. Okay? Now, I'm going to give you 2 formulas because there are 2 variations. One, if you rotate with respect to something that's parallel to the x-axis, and then another one if you rotate with something that's parallel to the y-axis. Okay? So I'm going to write 2 columns here. Because it's the same thing, it's just that something's going to be in terms of x and the other one in terms of y. But it's exactly the same thing. So rotation about, let me say, axis is parallel to the x-axis. So axis of rotation. It doesn't have to be the x-axis itself, just a line parallel to the x-axis. Axis of rotation parallel to x-axis. And then over here, let's develop the formula. If the axis of rotation is parallel to the y-axis. Okay, so we have a region. Let's say we have a region here, and then here we have a horizontal. So parallel to the x-axis means horizontal axis of rotation, right? That's what it means to be parallel. And we are rotating this region. Again, the idea is that we're going to fill this with a bunch of rectangles. So I'm just going to take a typical rectangle here. So we're going to fill this with a bunch of rectangles. And then after you make the rotation, I'm not going to draw the solid, but you understand the solid is created. That's going to be filled with this. Now, what data do we need from this disk? We need the radius of the disk, which is the height of your rectangle, right? We need the radius of the disk, and we also need the width. The width. Now, this width, because this is perpendicular to the axis of rotation, notice that to approximate, you're going to move left to right. Yes? So our variable, the variable that's changing here is, what is it? Is it x or is it y? It's going to be x. So I'm going to call it delta x. Okay? So this is going to happen from A to B. Now, let me do a parallel picture here. So let's say that we have something like this. Here we have the y-axis, or something, a perpendicular axis of rotation, something parallel to the y-axis. And now we want to rotate this region about this perpendicular axis. Once again, we're going to place a rectangle. We're going to fill this with a bunch of rectangles. Let's say this is a typical rectangle. This time, when we rotate, right, our disk is going to be like this, in the horizontal way, right? So now R looks like this, and then the thickness of the disk is, what is it? It's delta y, right? Because our variable of integration is y, because we are cutting like this from bottom to top. To fill the region, we need to move from bottom to top, right? So as delta y, and let's say that this is happening from C to D. We okay with the setup so far? Okay, so again, the idea is after rotation, In any of the two cases, after rotation, our solid is filled with disks, n of them, because we're going to have n rectangles, right? With this, and the sum of these volumes, and the sum of their volumes approximate our volume. The more this we use, the better is the approximation. Now, let us talk about a typical disk, and the ith disk. For example, this disk right here. At this point, I'm talking about the x-axis, the red picture. So at this point right here, if you move the place in which you place the rectangle, the height, the quantity r is going to change accordingly. It changes by looking at the curve that we have here above. Do you understand this? So it means this is naturally a function of x. Depending where you decide to place the rectangle, that's the r that you get. So the value of x is important, so that's not a constant. So r is really a function of x. Do you understand this? And similarly on the other picture, then depending where I decide to place my rectangle on this vertical axis, then the length of this rectangle may change. Yes? So this is a function of y. So r is really a function of y. And remember, in the vertical picture, that's in this picture is in the first one, the red is top minus bottom to find r. In the blue picture is right minus left. It's always the same thing. Okay. All right. So with this notation, we have that the volume of our solid can be approximated by the sum of the volumes of the, I'm gonna call it delta VI, the volume of each of the disk. But now we have a formula for that, right? So what's the formula for the volume of a disk? That's gonna be pi r squared times their width, right? So here, this delta W will be delta X in the red case. This will be delta Y in the blue case, okay? Just I'm doing two things at once here. So we take infinitely many disks by taking the limit as n approaches infinity, and therefore an interrupt pops up. So if you want to get the exact volume, we take the limit as n approaches infinity of the sum of all of these guys. And remember, this is a function. This right here could be a function of x in the red case, but then it could be a function of y in the blue case, okay? And similarly, this could be delta x or delta y, depending on the situation. Moral of the story, we obtain that in the red case, the volume is going to be the integral from a to b of pi r of x squared, and delta x becomes dx. In the blue case, we get that the volume becomes the integral from c to d of pi r of y squared. Delta y becomes dy. Okay? So this is the formula for the volume when the axis is parallel to the x-axis. So axis of rotation is parallel to the x-axis. And this is the formula when the axis of rotation is parallel to the y-axis. Okay, so these are the formulas that you really need to know, but you need to understand the setup, because from this setup, you know, what is it that you really need to know from here? You need to know how to compute R. So when your axis of rotation is parallel to the x-axis, you have to integrate with respect of x. If you have it with respect of the y-axis, if it's parallel to the y-axis, you need to integrate with respect of y. That's the first thing. Second, how do you find R? Look at the picture, okay? Because if you're trying to memorize a formula, like the way the book does, for example, the book is very, for example, if this is the x-axis, then the formula is always whatever equation this function has up here. And if this is the y-axis, the formula is whatever equation this curve has. But what if this is the line y equals 3, right? Then it's no longer that, so you need to adjust it. So the easy thing is you have your region, you need to sketch the region anyways. Then go ahead and place your rectangle and look at the picture and figure out how you can find the length of this rectangle, or the height in this case. Remember, in this case, it's always top minus bottom, right? It will be this top line minus whatever this line is. If it's the x-axis, then it's 0, and then you don't do anything, right? It's just the curve on top. But it could be between two functions and all of that business. Okay, anyways, those are the basic formulas. So let's do examples now to see this in action. Okay, do you understand the setup? Notice that the reason why we're using this is called the this method, by the way. This collectively, this is what we mean by the this method to find volume. And it should be clear why, because we are approximating the volume with this, right? Okay, so let's do examples. Oh, and even though I said it above, let me stress this, remark. The rectangle here is perpendicular to the axis of rotation. And as a general rule, because usually one confusion that students have is, should I use x or y to integrate? Well, whatever axis your rectangle is perpendicular to, that's always your variable of integration. Okay? Whatever axis your rectangle is perpendicular to. Okay, so let's do examples. So let's see. So find the volume.
Professor,
Yes.
you said just previously that if the axis of rotation is not like the x or y axis, like if it's x equals 3, we would do our function minus x equals 3.
We would do examples with that. Actually, this first example does that, so don't worry, you will see. So find the volumes. So find the volume of the solid obtained by rotating the given region about the given axis. Okay, so number one, let's see, I'm gonna give you the region and the axis. Let's say that the region is given by the function 2 minus x squared and the function g of x equals 1, and then we're gonna rotate about the line y equals to 1. Okay. All right. So again, step number one, sketch your region so you can see what's going on. Okay. You don't really need to draw the solid itself, but we need to sketch the region to really understand. Okay. All right. So let's see. Let's draw the function f. So this is a parabola, right? That's facing down and it's shifted up 2 units, right? That's negative x squared plus 2. So the vertex is up here at 2. Let's say this is 1, this is 2. And then the intercepts are a little, plus or minus square root of 2. So that's a little bit more than 1. So let's say somewhere in here, somewhere in here. This is our function f. Everybody okay with this? That's f. It's a parabola facing down, shifted up 2 units. Okay, and this is square root of 2, and this is negative square root of 2. Okay, so next we have the line y equal x, g of x equals 1. So that's the line, right? Y equals 1. So that's this one right here. That's a horizontal line. So this is g of x. And therefore, because it didn't say anything else, that means that the region that we are rotating is this one right here. It's a one bounded by these two functions. So between the graph of f and g. So we're talking about this region. You understand this? And we are rotating about the line y equals 1, which happens to be g. So we are, let me use another color for the rotation. And we are rotating about this line. So we get some sort of, it's not really a ball, but you know, because you know, this is not a perfect half. This is not half a circle, but you could imagine that we're going to get something that looks like a football or something like that. Yes? All right. And we want to calculate the volume or something like this. So to really understand the region, we should really know what is this point and what is this point, right? Because we need to know the beginning and the ending of the region. Yes? How do we figure this out? By sending the functions equal to each other, right? So let's find that out. So I want to know when f of x equals g of x. So 2 minus x squared equals 1. And now we solve. So what is this? We get x squared equals 1. So x is plus minus 1. So right on the mark here, more or less. You should move a little bit. This is -1, and this point here is +1. Yes? So this happens at x equals 1, x equals -1. Now we know exactly what the region is. Next, we need to place a rectangle. Remember, we're using this method, so rectangles always go perpendicular to the axis of rotation. There is no other option. So I'm going to place a typical rectangle. You place it wherever you want, okay? Notice that in this case, the situation is always the same. The top function is the red curve, and the bottom function is always the blue, right? Regardless where you place the rectangle. Okay, so in this picture, you know, it's good practice to put all the quantities that you need. So this is what R is, okay? It's the height of the rectangle. And then we know that the width of the rectangle is given by delta x. Okay, so first, we're gonna be using, let's start creating this habit, because there will be several methods later on. So you should always say what method you're going to use, because after that, that tells you what formula you need to use and so on and so forth. So right now, there's only one method that we know. So we're going to use this method, okay? Next, we need to know what's our variable of integration. So everything has to be written in terms of this variable. What's the variable of integration? X. The variable is x. So what do I need? I need this method. So I'm using this method, so that means I need to know what's r of x, right? Because everything else in the formula is a constant, which is pi. That's it. So back to the picture, and let's figure out what is r. Who can tell me how can we calculate r?
F of x minus g of x.
Right? Top minus bottom. Yes? So r can be calculated by doing the top function minus the bottom function. And we can do this with one integral because it's always the same situation. The situation doesn't change. Do you understand this? All right, so let's compute this. So that's 2 minus x squared minus 1. So that's 1 minus x squared. So the formula for r of x is 1 minus x squared. Are we good with this? So we are ready. So because we're using this method, we understand what the formula is. The formula is the integral of, let's see, from where to where? From where to where is the region? From -1 to 1. And then remember the formula is pi r squared dx. Again, this is the area of the base, and dx stands for the thickness. So you can remember this. This method, the volume of the disk, remember, the area of a circle times the thickness of the disk, which that's what dx represents. So this is going to be the integral from -1 to 1 of pi times 1 minus x squared dx. Do you understand this? Okay, now here, before I continue, let's do some observations just to save time when it comes to computations. Notice that this function that we're integrating is an even function. Do you remember what an even function is? No. So even means that the graph of this is symmetric with respect to the y-axis. The way you can check that from the formula is if you replace x by -x, if the y doesn't change, if the y doesn't change, then your function is even. For example, if I put a -x here instead of x, the square will kill the negative anyway. Anyways, understand this? So what that means is, let's go back to the picture. You know, parabolas are symmetric, right? We didn't do anything weird. Parabolas are symmetric, lines are symmetric. So this half from 0 to 1 is exactly the same thing as from -1 to 0. Yes? So if I calculate from 0 to 1, that would be half of my volume. So if you multiply by 2, that's the entire volume. Yes? So when you have an integral like this, that is from -8 to 8, in this case from -1 to 1, and the function is even, you can replace it and do from 0 to 1, but then multiply by 2. And why am I doing that? Because it's easier to plug in 0 than to plug in -1. Plugging in -1 is a pain, then you have to do more calculations. Okay? That's just something to make it easier and to remind you of this property. So let me make the note here that this is an even function. So even means, okay, I'm not going to use f because we already have a notation for f. But even means that when you plug in -x into the function, you get back the same formula. Okay, that's what it means to be even. And so I can do the integral from 0 to 1. So I'm going to do only half of it. But then, of course, I have to multiply by 2. Okay? And again, I'm doing this for convenience only because it's easy to plug in 0 and negative. All right. So how can we calculate this integral now? Now let's compute the integral. How do we do this?
You move the pi out.
Yes.
And then you square 1 minus, or you could use substitution.
Do we have an x?
Oh, no, you don't. So you've got to square.
Exactly. So here the plan is we expand the square and then we use power rule. Yes, we get a degree 4 polynomial and then we use power rule. Good. That's what I'm going to do. So take out the pi and then let's expand the square. So that's 1 minus 2x squared plus x to the 4 dx. And then let's calculate this. So that would be 2 pi times, now this is x minus 2 times x cubed over 3 plus x to the 5 over 5, and then from 0 to 1. And then this would be 2 pi times plugging 1, so you get 1 minus 2 over 3 plus 1 over 5, and then the other term is 0. You see, if we didn't do this little trick here, then you will have to plug in -1 here and then have to combine all that. Not a big deal, but it's just more work. Okay, so now we're ready. So that's 2 pi times, let's see, 1 minus 2 over 3, that's 1 over 3. So 1 over 3 plus 1 over 5. Multiply this by 5 and multiply this by 3 to get the same denominator. So as 5 plus 3 is 8. So we get 2 pi times 8 over 15. So the final answer will be 16 pi over 15. All right, questions?
Where did you get 2 from really quickly?
Okay, did you understand what I said about even functions? A function is even, what it means is that its graph is symmetric with respect to the y-axis. The y is like a mirror. Look at this picture. From 0 to 1, this part right here, even though it doesn't look symmetric, I kind of draw this a little bit bigger, but this is a parabola, so you know parabolas are symmetric. So whatever happens here from 0 to 1 is exactly the same. This part right here is a mirror image of this one. If you fold it along the y-axis, the two pieces will overlap nicely. Okay? So basically what we're doing is, okay, let's just calculate from 0 to 1 because the solid, this is half of the solid. From 0 to 1, you have half of your solid. So let's calculate that, but then do times 2 to get the whole volume. Okay. Because from 0 to 1 is only half of the volume. That's why I put times 2. And you can always do that when you integrate an even function, and the limits of integration are like this, from -a to a. So -2 to 2, -5 to 5, right? When that happens and your function is even, you can just do from 0 to whatever number you have, but then you need to do times 2. That's the problem. So let me say here, remark, if f is even, meaning f of -x equals f of x, then the integral from -a to a of f of x dx equals 2 times the integral from 0 to a. That's the property I'm using. Okay? Now, since I'm here, what if f is odd? What happens to that integral?
No, then you can't substitute 0.
What does it mean to be odd? Odd means that the function is symmetric with respect to the origin. So whatever happens, let's say up here in quadrant 1 is going to reflect down here to quadrant 3. The same thing that happens on top of the x-axis is going to happen below. So what does that mean? But it means that you're going to get the same number, but this is positive and this one is negative. So they will cancel each other out. So when you integrate an odd function, the integral is always 0. Okay? So the other property is if f is odd means that f of negative x is minus f of x. Okay, that you can pull out for the typical example here is x squared. The typical example here is x cubed for an odd function. Okay, when that happens, then the integral from negative a to a of f of x dx, this is always 0. Those are quick things that you can do to speed up your computations. Okay, and you can calculate as usual, but you know, this is kind of helpful because if you have something that's super complicated, but the function is odd and the limits are like that, you know the answer is 0. You don't even have to worry about solving the integral. And what happens is that one piece of the function is positive, but the other one is negative. So this piece of the integral is going to be positive from 0 to a. This piece from negative a to 0 is negative, but it's the same number in absolute value, so they cancel each other, giving you 0. Okay. All right. So for example, the integral from negative 1 to 1 of x cubed, that's 0, without having to compute anything. You can try on your own, but that's 0.
X cubed?
Yeah, because it's odd. That's and like x cubed, I could say arctangent, for example, the integral from negative pi over 4 to pi over 4 of the inverse tangent. The inverse tangent is an odd function. You need to have knowledge of the function to be able to do this, right? But this is an odd function, so without having to worry about how do I even calculate this integral, I know the answer would be 0. Because inverse tangent is odd. Okay? Okay. All right, but back to the volume. Questions? No? Okay. So again, I didn't kind of mention this earlier because this is typically you talk about this at the beginning, Cal 1, at the beginning of integration. Cal 1, when you talk about properties of integrals and so on, then you also bring up this because this is a nice little technique that you can use. Okay. All right. So how about this one? So the region is f of x equals square root of 4 minus x. And then is bounded also by the x-axis over the interval from 0 to 4. Now, when I say this, notice that everything is in terms of x. So I mean from x equals 0 to x equals 4. Okay, this interval is referring of the x-axis. And let's rotate about the y-axis. So remember, our first job is to sketch the region. All right, so let me make a few comments on the function f. This is the same thing as saying square root of negative x plus 4. This is something that you used to do back in college algebra, okay? And this is square root of minus x minus 4. Now, why am I doing this? Because this is to be able to figure out what transformations are happening to this function. This is the square root function, and there are two transformations to it. The first one, this negative here, what it does is it's a reflection with respect to the y-axis. When you replace x by negative x, this is the sequence of transformations. You start with your square root function, then you replace x by negative x, and then you replace x by x minus 4. Okay? Those are the transformations that are happening. The first one, this is a reflection. This means reflect about y-axis. So you flip the graph with respect to the y-axis. And the next one, when you replace x by x minus something, that means shift to the right that many units. So that means go to the right 4 units. So shift right 4 units. Okay? Do you remember doing transformations some time ago? Okay, we're using that here now. All right, so now we understand what the graph is. It's a square root graph, but it's being flipped, shifted to the right 4 units. So remember, typically a square root looks like this. So what's happening is we are flipping it like this, and then we're bringing it to the right like this. Okay? So I'm just gonna draw here the final version of it. Let's say that this is 4. So 1, 2, 3, 4. So it starts here, and then the y-intercept is when x is equal to 0, which is 2. So square root of 4 is 2. So right here, 2. And looks more or less something like this. Yes? So as a function f. Are we good with this? Look at the transformation. Square root function it looks like this, right? Then you shift it, and you have to reflect with respect to the y-axis. So now it looks like this, and then pull it to the right 4 units. You get this picture. Okay. All right. Next is that the x-axis. Okay, we have the x-axis here, and then over 0 to 4. Okay, so we're talking about this region right here. So it begins at 0 and finishes at 4. Yes? And we're going to rotate about the y-axis. Okay, so the rotation is happening like this. We're rotating around the y-axis. So remember, we need to place a rectangle perpendicular to the axis of rotation. So our rectangle must be placed like this. Okay, the moment that we have the rectangle placed, then we immediately can write several things. So first of all, there is no hole, so the method is disk. What's the variable? The variable is y, right? So, by the way, by just writing this down, you can immediately write down that the formula is going to be, let's see, what are the limits? From where to where?
0 to 4.
From 0 to 2. Look at the variable. What's the variable? Y, so you have to look at the y-axis. The region goes from 0 to 2, right? From 0 to 2, and because it's this, you know, it's pi out of y squared dy. Just by writing that we're using this method and the variable is y, you can immediately write down this formula. Now, to proceed any further, we need to know what is out of y, right? We need to know what is this. So, let's go back to the picture and understand what is r. Remember, r is the radius of your disk, which is the length of your rectangle, right? So this is r, right here. That's what we mean by out of y. So how can we calculate out of y? It will be right minus left. What's the right in this case? The function, well, f of y, right? We need to write everything in terms of y. So that means that we need to go and change the formula a little bit, right? That would be the right curve, but in that case, we need f of y. And then the left curve is just 0. So this is just given by f of y. Do you understand this? Because the left is the line x equals 0. So it will be, if you want, minus 0, right? Which is just f of y. So let's figure out what's f of y. What is f of y?
Negative y squared plus 4.
So 4 minus y squared. Okay. Right, so we have over there, here is how you find it. So you know that y equals square root of 4 minus x, so for x. And then you have x equals 4 minus y squared. Yes? So f of y is going to be 4 minus y squared. So that makes, tell me the y, and then I will tell you what x you have. Okay? So that equals 4 minus y squared. And that's what we integrate. So that would be the integral from 0 to 2 of pi times 4 minus y squared dy. Questions?
Yeah, how did you get the y-intercept? Like, how did you get to as where you?
How do you find y-intercept of a function? You make x equals 0, right? Remember, this is a point on the y-axis, so every point on the y-axis has x equals 0. You put x equals 0 here, and you get square root of 4, which is 2.
What about the other two? The -2?
What do you mean negative 2?
When you square root it, you get 2 -2. So
No.
it doesn't. It goes into.
Square root of 4 is 2.
Right, but also square root of 4 is also -2.
No.
-2
This
is
symbol means I want the positive answer. You're thinking about something else. You're thinking about solving this.
for the 0.
X squared equals 4. This is what you're thinking.
Yeah.
Okay, so the square root is not there. Now, the solutions here are 2, plus or minus, but notice how we always write square root of 4. But you have to manually put the plus or minus. If I tell you square root of 16, what's the answer? What is it? 4. It's not negative 4. Right? And so we already have our square root there. So put 0, and then it's square root of 4, which is 2.
Okay, got it.
That's it. Yes? Okay. So to be technical, yes, this graph here is given by 4 minus y squared, but if you write this by itself, this is really the entire parabola. So you have some restrictions, right? So here you need to say that this happens as long as you want the upper half of the parabola. So this is for x. I'll just say x greater than or equal than 0. Okay? Which would mean that it comes over here and then it will tell you what is it for what. But basically I'm saying I only want the upper half. But that's just a technicality that you don't have to worry about that one. Okay, so do you understand how we got this formula? Now it's just calculating this. We calculate this the same way that we did the other one. Okay, take out the pi, square this, and then power rule. So integral from 0 to 2, so this will be 16 minus 8y squared plus y to the 4 dy. So this is pi times 16y minus 8y cubed over 3 plus y to the 5 over 5 from 0 to 2. Okay, so we have to plug in 2. So it's gonna be 32 minus, so 2 cubed is 8 times 8 is 64, so it will be 64 over 3 plus 2 to the 5, that's 32. 32 over 5, that's what we get when we plug in 2, and then when we plug in 0, everything has a y, so we have 0. All right, so we need to do this painfully. Okay, so let's see. So I'm doing it, so don't complain when you have to do it yourself on the homework and all of that, right? I am doing it.
I have two notebooks, so it's
So let's see, 32 times 3, so I'm going to multiply here top and bottom by 3. So 32 times 3, that's 96, right? 96 minus 64, that is 32. 96 minus 64 is 32.
Yeah. Yes.
So that's 32 over 3. Yeah, that's nice. So that's 32 over 3 minus 32 over 5. Yeah. I want the same denominator, not the same numerator. Yeah, it's to see if you're paying attention. Sometimes I will do this to see if you're paying attention. Okay, so times 5 and then times 3. All right, so what is this? So 32 times 5, that's 10, so 160, and 32 times 3, that's 96. 160 plus 96. 160 plus 96, so that's 256. So that would be 256 over 15 pi. All right. Anyways, you can check it with your calculator, make sure that I didn't force anything there. Okay, questions?
So, when using this method,
Uh-huh.
can you interchange all the methods, or do we always have to, is it always going to be a specific one for a specific style of question?
What tells you what method to use is how you place a rectangle. Right now we're doing this because it's the only one that we have discussed. But later we're gonna talk about the Watcher's method, which is when we have a hole, which we're about to do pretty soon. And then we have the cylindrical shells method. That one is different. That one, the rectangle has to be placed parallel to the axis of rotation. Sometimes it's more convenient. In this same problem, you could have decided to put the rectangle like this. Okay, parallel to the axis of rotation. But then the formula is different because what you get inside your solid is something different. And sometimes it's more, you know, this was easy, but sometimes it's easier to do it the other way. So that's what we're going to start in 2.3, how to do the volume by cylindrical shells. Then at the end, you are given a problem, you decide what you want to use. So the first thing is you draw a region and you place your rectangle, wherever you think is more comfortable for you. The position of the rectangle tells you the method. Perpendicular to the axis of rotation, this method, or Watchers, if there is a hole. And then if it's parallel to the axis of rotation, it's cylindrical shells. Okay? And once you know the method, then that will tell you the formula to use. And then you find the stuff that you need to find. But right now, we only are discussing this method, which is what we have so far. Okay? That's why, I am trying to give you these steps. First, identify the method. First, the rectangle. Then that will tell you the method and the variable. And after that, you know the formula, and then you find what you need. Okay? All right, so let's see. How about the region is given by g of y equals y, the y-axis, and this happens over the interval 1, 4. Now I want you to understand everything here is given in terms of y. So when I say over the interval 1, 4, this is on the y-axis, this interval. Okay, and then okay, I wanted the top problem to be about the x-axis. I confused it with okay, it doesn't matter. We did it about the y-axis. Okay, this one is also about the y-axis. Originally, I wanted the top problem to be about the x-axis, not about the y-axis. But that's okay. We did it about the y-axis. Anyways, let's do another one about the y-axis. Here it's kind of clear that I want it to be about the y-axis because I'm giving you the function already in terms of y, right? So remember that this right here is the same thing as saying x equals y, okay? The same way that we say f of x is the same thing as y. If you have f of y, that's the same thing as x, okay? So this means that's the line x equals y. All right, let's draw it. So as x equal to y, so here is g, that's g of y equals y. Then the y-axis, and then from 1 to 4. Again, everything is happening on the y-axis, right? So 2, 3, 4. So that's the region that we are rotating, and we are rotating about the y-axis. Rotating like this, okay? So we need to place a rectangle perpendicular to the axis of rotation. That's the only thing that we know right now. And will be the correct way to do it anyways. And so immediately we can say the method, which is this method, and we can say the variable. What's the variable? The variable is y, and with that data you can come here and write down the formula. So what's the formula? From where to where is the integral for the volume? From 1 to 4, and the formula is?
1 or pi times y squared.
Okay, the formula. So pi out of y, right? Square dy. So then I'm telling you how you should approach this in general. Then we need to come back to the picture and figure out, okay, what is r of y? Well, in the picture, by r we mean this right here. And just like before, r is calculated by doing right minus left, right? So r of y is the right picture, the right curve minus the left curve. The left curve is 0, but g of y happens to be y. So like your classmate is pointing out, r is just y, okay? Plug in. And then we integrate. Okay, questions on the integral? All right, so now we do this. So that would be y cubed over 3 from 1 to 4. So that's 4 cubed, that's 64. And so we get 63 over 3 pi. And we can simplify this as 21, right? So 21 pi. Okay, questions? Huh?
Can we do a practice by ourselves while you do attendance?
I already burned the practice. It should have been this one. Okay, I mean,
Just for one time or so.
Let's see, we have time. We have time. So
If I make a mistake.
I'm gonna explain watchers, and then you're gonna practice with watchers. It's the same thing. It's just that you need to take into account a hole. So how do you think we're gonna take into account a hole? Imagine a dish with a hole. So you're gonna have an outside dish and an inside dish. The inside dish represents your hole. So you subtract pi r squared from the outside minus pi r squared from the inside. And that's it. It's the same thing.
That sounds,
This is outside volume minus inside volume. That's it.
I need to see.
That's exact. So it's just that if not, you can do the same problem, but this is already done with the region, right? But you could do this about the x-axis. Okay, so let's do the following. While I take attendance, do problem 2, but I'm gonna change it. Instead of being about the y-axis, do it about the line x equals 1. Okay, so do it about the line x equals 1.
Wait. So which one?
So let's see. No, because that would be then rotating about the y-axis. So rotate about the x-axis, so you do something different, but then rotate about the line. But we already did the rotation horizontal, so let's do it vertical. Okay, so same thing about the y-axis, but rotate about the line. But then the region is gonna be from 1 to 4. Instead of being from 0 to 4, it's gonna be from 1 to 4.
Okay, it's the same for me.
Okay, and then I want you to rotate about the line x equal 1, not about the y-axis. So let's see, number 3. Just set up the integral, don't calculate. Okay, so number 4, the region is gonna be, or maybe let's see, shall I change something? Okay, let's make something more interesting. Let's make something more interesting. So let's do f of x equals, but I have to be careful. It has to be something that you can integrate. Yeah, it has to be something that you can integrate. So because we haven't done anything with exponential and logarithm, so I want to bring this. I have to be careful because you know how to integrate e to the x, but you don't know yet how to integrate ln of x. We need to talk about integration by parts to know that. So let's see. We can do ln. Okay, so we can do ln of x. And then the region is going to be bounded by ln of x. Then we can do y equals 1. So we can do from y equals 1. It's always nice to put e, so let's put e.
You get too excited about this.
let's see from y equals 0. Let's see from y equals 0. If we put 1, it's gonna be nice. So let's make it easy. So from y equals 0 to y equals 1, and then we have that the y-axis, and then rotate about the line x equal 1. Yes. Okay. Do you want me to draw the region for you so you can see how it is? So remember how ln looks like. ln looks like this. Right? This is the ln function. Now, what is this point right here? That's 1, right? Then I want y equals 0. That's the x-axis. Then y equals 1. Let's put it here. That's y equals 1. Who is this guy? What's the x value for this point?
2.
ln of what equals e. Good. And that's that. And then the y-axis. So the y-axis. Okay, I want more. Sorry. And then x equal 1 to make the region, because I want this piece here. X equal 1. That's a vertical line. That's this one over here. Right. So this is the region. Right. That little piece right there is the region, and then rotate about the line x equal 1. So rotate about this line. Okay, because if I didn't put the x equal 1 here, then I will be talking about the whole thing all the way up to the y-axis. But then you will have about this line, you have overlapping stuff. That's actually very complicated. Yeah, actually, I think what's going to happen is that this is not going to matter. Just this piece right here is going to override whatever this does, so you're going to have the cylinder anyways. You know, it's like you only need to rotate half a circle to get a ball, right? But you could rotate an entire circle also, and you get the same ball. It's just that the ball is being rewritten itself twice. The upper half and the lower half, they overlap each other. Do you understand what I'm saying? You have more layers if you think about it. That's the same thing happening here. If I would have said, if I didn't put x equal 1 here, it would be all of this piece here to the y-axis. When you start rotating about this line, specifically x equal 1, this rectangle right here, or square, really, is going to overlap with this, and actually is going to, well, this is not 2, this is 2 point something. Okay, so it's gonna, there'll be this little piece here that's gonna, it's more complicated. So I'm just trying to tell you that there's a reason why I decided to put this x equal 1 here, okay? Otherwise, it will be more complicated, the problem. Just to simplify the read. So remember, place your rectangle perpendicular to the axis of rotation. Your variable would be y, yes, because your axis of rotation is vertical. Now you can see from here your limits. What are the limits? From where to where?
From 1 to 0.
From 0 to 1, right? From 0 to 1, but then you need to write everything in terms of y, right? That's why I choose ln, because then when you write in terms of y, what do you get? E to the y. You know how to integrate that, right? So, go for it.
Wait, so we're rotating about x equals 1 or y equals 1?
X equal 1, which is this blue line right here.
Right.
So remember, place your rectangle, which will be like this, right? And then do the problem. Okay, let me take attendance. All right, so remember, those of you that are on Zoom, when I say your name, remember to type here on the chat. All right, Carl Abby, Gisela Costa, Christopher Araujo, here, okay, Elena. Okay, did I say it correctly? I think last time I got it wrong. I'm not sure if I say it correctly this time. But okay, you're here. Corina Cardenas. All right, okay, I'm learning. Jason Carver. Okay, Ángel Concepción.
Here.
Joel Correa. Andy Diaz. Okay, here. Melanie Gavilanes. Warsandy Gefrat or Gifrat. Okay, here. Daniel Herrera. Adam Hirschon. Franklin Yanes. Zina McKean. Joshua Miller.
Here.
Paul Monroe.
Here.
Orangel Olmos.
Here.
Guillermo Piedra. Okay. Robert Sarabia. Kyle Silvera. Laura Sayas. Okay, good. All right, so let's set it up. Okay, so let's did you have time to think about the problem? Yes? All right, let's see. So you understand? So first of all, let's keep the routine. That way we don't forget. What's the method? The method is this. What's the variable? The variable is y. So we immediately can write a formula. So what's the formula? From where to where? From 0 to 1, right? Look at the y-axis. We're moving from 0 to 1 of pi out of y squared dy. Yes? So now we just need to figure out who is this guy. That's out of y. Let's go to the picture. What is represented by out of y in the picture?
The blue rectangle.
But what part of the blue rectangle? The length or the width?
The length.
The length. So, literally do this. Just write it down so you can visualize it, so you can see it. The picture will tell you what's the formula. Okay? But you need to write it down. Let's see. Andy says that he's here. Okay, so who can tell me what's the formula for out of y? So I got you, Andy. So what would be the formula? So let's see. We need to, first of all, we need to write everything in terms of y, right? So let's make sure that we have all the formulas in terms of y. So here, this is f, but we really want to have it as f of y. What's the formula for this in terms of y? E to the y. Does everybody understand this? Remember, here you have y equals ln of x. This is f of x equals ln of x, right? I'm talking about this function, but we want to write it in terms of y, so that means you need to solve for x. So if y is ln of x, then x is e to the y. Yes? That's where we're getting that from. Okay, so that's y, and then okay, that's it. That's that. Okay, now we need to write out of y. Who can tell me what is out of y?
E to the y minus 1.
Very good. Remember, right minus left. Yes? The right curve here, remember, really, this r right here is basically this little piece on the x-axis, right? This is what we're trying to calculate, right? So you will do this by doing right endpoint minus the left endpoint. Now, if you think about it, this starts at 1 and then it goes all the way up to here. Now, the right endpoint is this x value, but it's from 0 all the way up to that piece. Yes? So you have to remove this constant piece that is always 1. Does that make sense? So that will be whatever this is, which is given by e to the y, and then you have to do minus 1. We have to take away this piece. If you only say e to the y, you are actually calculating all of this. If you only say e to the y, you're calculating all of that distance. You have to remove that piece, which is 1 all the time. Do you understand this? So it's always, left minus right. Okay, so that is e to the y minus 1. Is this clear? All right. Oh, we're square. We can also integrate that. Just I have to be careful because since we haven't study any advanced techniques, we have to make sure that we get something that we can solve, but this we can solve. All right, and that's all we need. So integral from 0 to 1 of pi times e to the y minus 1 squared dy. Are we okay with this? So this is really what, do you want me to solve it or are we good with this? Should we solve it?
Can you solve it?
Okay.
Just integrate. You don't have to do the definite. Just integrate. Like you don't have to like solve all the way to the final.
If I do that, then might as well get the nice number.
Okay, well, fine, whatever.
So here the idea is let's expand the square. So it would be e to the y squared. That's e to the 2y, right? Minus 2e to the y plus 1 dy, and then integrate. So what's the antiderivative of e to the 2y? Very good. So e to the 2y over 2. Remember, you need to take into account chain rule. So the times 2 that comes from chain rule, you need to compensate by dividing, right? So the formula is integral of e to the ax dx. This is 1 over a e to the ax. That's basically what I'm using. Okay. Okay, so that's that, and then integral of then minus 2 times e to the y, the integral of e to the y is e to the y plus y, and then from 0 to 1. So we get e squared over 2 minus 2e plus 1 minus, now when you plug in 0, be careful, you don't get 0, right? Because e to the 0 is 1. So you're going to get 1/2 minus 2 plus 0. And then we calculate this. So that would be, and we combine something nicely here. So as 1/2 e squared, that stays like that, minus 2e, and then we're gonna have here, this is positive 2, so that's a 3. 3 minus 1/2. What's 3 minus 1/2? That's 5/2. 5/2 plus 5/2. Right? Like don't ask me. And then that's it. We cannot do much here, so we stop there. Okay, but again, really the important thing is to be able to set this up and to get this integral right here. Okay, then the rest is just computation. Did you understand this?
Yes, sir.
All right. Okay, so here's what I'm gonna do, because otherwise we're gonna be delaying. I'm gonna do one more example of using watchers. So I'm gonna use the example to explain you how to do it. Next time, I'm gonna write the formula and do the whole thing, but you know, so that you can get ahead with the homework and start working on those problems, okay? So, and then we close with that one. So let's do that one. So let's motivate this with the following. So a watcher is obtained when we rotate a rectangle. So the idea here is that when you rotate a rectangle, just so you understand quickly, imagine that you want to rotate a rectangle once again, but this time, this rectangle is away from the axis of rotation. There is a little space between the rectangle and the axis of rotation, okay? If we do that, what's gonna happen when you rotate? So naturally, this top part of the rectangle is going to create a big disc, yes, but then this bottom part of the rectangle, this gap right here, is going to create a small disc inside. That's a hole, because really the region that we're rotating is this one, so there is a hole that we are, that we're missing. So basically, we're going to get something like this. So we're going to have this, but then we're going to have here an inside. Okay, so basically we're gonna have an outside dish, but then this is gonna have a little hole in the middle. Okay, now there are some quantities here that are important. So we want this. It's okay. So we want this. I'm gonna call this capital R out. Why? Because the top of the rectangle all the way up to the axis of the rotation, okay, even including the hole, all the way, that's the radius of the outside disc, right? The outside disc, here is the center of my disc. The radius of the outside disc, all of this, that's R out. And then this little piece, the distance between the rectangle and the axis of rotation, I'm gonna call it little r in, because that's the radius of the inside disc. Do you see this? So that's this piece right here. That's what R in is. So naturally, this is called a watcher. So same idea. So what's the volume of a watcher? So the volume of a watcher is gonna be, the outside disc, volume of the outside disc. That's pi r out square. We have some thickness here times delta W. But then that's the whole big disc. We need to take away the inside disc. So minus pi r in square delta W. We can factor out here pi, and typically we put the width here, and then we just subtract r out square minus r in square. So moral of the story, the way that you deal with problems like this is exactly the same thing as this method. It's just that if you have a hole, then there is an outside radius, there is an inside radius, and the formula you integrate is this one. Pi times r out squared minus r in squared. And the W becomes dy or dx, depending on the variables of integration. Okay, that's it. So let's see if I will just set up the integral. I'm not going to solve it, but I will set it up. So for example, let's calculate the following. So find volume. And let's say that the region is given by the square root of x, 1 over x, and this is over 1,3, and we're going to rotate about the x-axis. Okay, so again, let's sketch. Okay, so we have square root function. So this is f of x, and let's say that this point right here, let's call it 1, right? And then we have 1 over x, which comes like this. You know, it has another piece down here, but I don't care about that other piece. So this is the piece. I mean, the other piece of 1 over x is down here, but we don't care about that, okay? So that's the function g, and then is from 1 to 3. Okay, let me put g here. Then it's from 1 to 3. So 1 is here. Let's say this is 2, and let's say this is 3. So f of x, g of x over 1 to 3. So that means that we're talking about this region right here. Okay, bounded above by f, bounded below by g, and then starts at 1 and finishes at 3. That's what that means. Okay, so f, g from 1 to 3. So we're talking about this region, and it's going to be about the x-axis. So now notice that this time our region is not adjacent to the axis of rotation anymore, right? There is a little separation. So when you rotate this, there is a hole here that's going to be creating a solid. Okay, so again, we're going to place a rectangle perpendicular always to the axis of rotation. This time when I say perpendicular, it means if you extend it, it will be perpendicular. Okay, so because there is a hole, then that means that the method that I'm going to use is Wacher's. Why? Because there is a hole and I put it perpendicular. What's my variable? The variable is x, because we're moving like this, right? It's perpendicular to that. And then the formula is going to be the integral from 1 to 3, because those are my limits. And then remember, it's pi r out of x squared minus r in of x squared dx. So it's the outside radius squared minus the inside radius squared. Now you just need to come up with formulas for those. So what's the formula of r out? Let's go to the picture. What is r out? R out is the distance from the top of the rectangle all the way up to the axis of rotation. That's r out. And r in is the hole, the distance between the bottom part of the rectangle and the axis of rotation. Now the formula tells you. Look at the picture. What's r out? How do I calculate r out by looking at this picture? I just give it the function f, right? That's it. R out is f, which is square root of x. And what is r in? R in is given by the function g, which is 1 over x. Do you see that? R in is this little piece here. That little piece is given by the blue function. R out is all of this that's given by the red function. Yes? If this is moved somewhere else, then you have to do top minus bottom. Here I'm also doing top minus bottom. This is the bottom is 0 all the time. That's why I'm there. And then you integrate that. So that would be the integral from 1 to 3 of pi, then square root of x. This turns out to be an easy integral, minus 1 over x squared dx. And here the square root cancels nicely, right? And then the next one is 1 over x squared, that you can do it by using power of, right? As x to the negative 2, and then continue that way. Anyways, next time I'm going to backtrack a little bit, write down the formula and so on, but hopefully you understand the idea. It's exactly the same thing as this method. It's just that there is a hole now. So there are two radius, the outside radius and the inside radius, okay? That's all.
Seems to be easier than this method.